Welcome. Now we're in lecture number 25. We want to talk about the generalization bound. And this is the outline of today's lecture. But first of all, let me give you an overview of what we want to do in the coming few lectures. This is the first in the series. We want to talk about generalization. And then we want to introduce a concept called the growth function. And then finally, we want to talk about a notion called the VC dimension. In today's lecture, I want to divide it into three parts. The first part, I want to talk about the problem of having a lot of hypotheses. So now your hypothesis set is not just one hypothesis, but now you have m hypotheses. In this case, then the Huffington inequality will not be able to apply. And so we want to understand what will happen when you have these m hypotheses together. Then the second part of this lecture, I want to talk about the generalization bound of how do we understand the behavior of a learning algorithm. Then in the third part of this lecture, I want to talk about what would be the techniques to handle all these m hypotheses. So let's briefly review what we have done last lecture. We talked about the notion of probably approximately correct. And if we recall, the probably correct framework says that I'm measuring the probability of certain events. And this event has to be lower bounded by a certain number. It will be 1 minus delta. This is called a probability correct because you're measuring the probability, so you're not absolutely certain. You're only measuring in terms of probability, therefore it's probably. It's correct because I have a notion called the confidence, 1 minus delta. Okay, so this delta here is called the confidence. Okay, so normally the delta is a very small number, and so 1 minus delta is a big number. Approximately correct measures the thing that's inside your probability. This is the probability of having E in compared to E out. That is very, very small. Okay, so E in is the in-sample error, E out is the out-sample error. You want to make sure that this error is very small. So if you can find an algorithm A such that for any epsilon and any delta there exists an n which can make the above inequality holds, then we say that the target function is PAC learnable. So I want to quantify the difference between a notion called a guarantee and possibility. This is a recurring framework in our machine learning work. Okay, normally when you think about a guarantee, a possibility, you think about I want to make sure that every case is possible. This is what we call the deterministic case or deterministic learning. Now the other case will be the probabilistic learning, which says that you can try to learn something using the training set to the testing set through the correlation between the two. So the deterministic set asks the question, can a data set D tell me something about F outside of D? Okay, so what is D? D is the training set. F is the target function. You ask whether the training set can tell you something about the target function that is outside your training set. Okay? And the answer is no, as we have seen in the example before, that you can only look at the 6 cases, but the last 2 cases you are not able to say anything. Okay, so anything outside the D is uncertain, it has uncertainty, and there's no way for you to deal with this uncertainty if you are in this deterministic mode. Now, the probabilistic mode is doable because you ask, can D tell us something possibly about F outside D? Now, let's look at the difference between these two notions. Deterministic asks absolutely correct. Probabilistic framework asks possibly correct. The difference between the two is that in the deterministic case, I want to make sure that even the worst case scenario is also guaranteed. That's why it's called a guarantee scenario. The probabilistic situation says that I only want to make sure that the probability of having F outside D is small or having a bad event is small. once you have this kind of probabilistic statement there, you are not able to claim absolutely certain, but you'll be able to say that it's probably correct. And therefore, if you're in this probabilistic framework, then the answer is yes. You can actually say that D can tell us something possibly about F outside the set D. So if the training set and the testing set have the same distribution P, then training can say something about the testing. And of course, we need to make an assumption that the assumption is that all the samples, they are independently drawn from the P. Now, I want to talk about the problem of one hypothesis versus the final hypothesis. So we call this equation, this is what we define the Hoeffding inequality. Okay, so that's the Hoeffding inequality. And in order to make this inequality to hold, we're assuming then the hypothesis H is actually fixed. So you give me the H, and then I evaluate this probability, and then I want to show that the probability of happening is extremely small. Okay, so this is Hoeffding inequality, and we like that, and we show many examples on that, and we talk about an example of a pack learnable using that this Hoeffding inequality. So we look at this, and now let's look at the problem more carefully. This H is actually chosen before you look at the data set. Okay, so what do I mean? Well, before you ever look at the data set, you have already picked the H. Now, if your H is chosen after you look at the data set, then this Hoeffding inequality is becoming invalid. Why? Well, think about this. Your H is one hypothesis. Okay, this is your hypothesis that you want to evaluate. If you have a set of hypotheses, then you need to run a learning algorithm A, and then this learning algorithm A will need to choose from a set of hypotheses and return you one. So in this situation, you will have a set of H, and you need to pick one. And when you are picking this one, then you are not just evaluating the probability of having that particular H. You actually need to consider all the possible H that are floating around. Okay, and so what it means is that we need to choose an H from the hypothesis set during the learning process. And then the H we choose really depends on the training set D, and the H that we are actually using here is the final hypothesis. So if you want to be more clear, that here in this equation, what I'm really analyzing is not one hypothesis that comes from that entire hypothesis set. I'm just evaluating the final hypothesis that for some magical reason someone gives you this G. Okay, then this Hoeffding inequality will be able to quantify what is the training error for this G, this final hypothesis, compared to the outsample error for this G. Again, if you have a set of hypotheses to choose from, we need to take care of all the possible hypotheses inside the hypothesis set. So if you need to choose a G from a set of hypotheses, H1 through Hn, then you need to repeat this Hoeffding inequality m times. Okay? And now if you want to repeat this Hoeffding inequality m times, then it's no longer this very simple Hoeffding inequality. We need to make a change. So what kind of change that we need to put into this Hoeffding inequality in order to capture this factor of m? So let's look at this equation. So the event that we are looking at would be the deviation between your in-sample error, E in applying to G, compared to E out applying to G. Okay? And we want to ask, what is the probability of having this event? Now remember that this G is the final hypothesis. This is the hypothesis for some magical reason someone gives you. And in order to get this G, what you really need is that you need to look at all the possible cases. Now what are the possible cases? It will be here. You have all the H1 through Hm. These are your possible choices of your hypotheses. Now, if you want to get to a G, this means that you need to choose either H1 or H2 or H3 all the way through HM. So, in other words, if I want to ever get a G, I need to evaluate the probability of getting all these cases or together. So to have G, you need to consider all these H1 through HM. And since you don't know which H to pick from, you need to pick an OR case, and you need to put OR among all the possible cases. And so here you have a sequence of OR cases, and then you need to put a probability on all these OR cases. So what do? Well, you can apply the following trick. So first of all, you start with the event that you are looking at E in of G minus E out of G bigger than epsilon. So this is the probability that you want to evaluate. Remind yourself that G is the final hypothesis. This is the hypothesis after the learning algorithm has seen the data sets and make the decision. So this is the final hypothesis that you actually want to evaluate. Now, the equation on the right-hand side will be what? Will just be the probability applied to all these n events. So how do we get to A? A is a statement as follows. If you have an if statement, okay, so if you have event A and B, and if probability of A, if event A will imply event B, then you can see that the probability of getting A will be smaller than the probability of getting a B. Okay, because whenever A happens, B will happen. Okay, but if B happens, A will not happen, and therefore B is a bigger set than A, and therefore the probability of having A will be less than the probability of having B. So same for here, you're looking at this event of G, in sample applied to G compared to out sample applied to G. This is the event that you want to consider, and since this implies the other sequence of all events, and therefore according to the identity here, I will have a less than or equals to. Now, given all these sequence of OR events, what you can do is that you can pull out all these events and turn it into a summation. Okay, so now what is the meaning of the summation? Well, here is a sequence of union of sets, and now you can apply what we call the union bound, which says that if you apply the probability to A or B, then the probability will be less than or equals to the probability of A plus the probability of B. And now if you apply this union bound to the equation here, then you can see that all the sequence of OR cases will become a summation of the individual probabilities. So now let's imagine that all these events, they are independent, and let's also recall that this one probability here is just the upper bounded by the half inequality, and the half inequality is universal. There's a power of the half inequality is universal, and therefore you just need to apply the half inequality to this event. Okay, and then all the half inequality will be the same, and so you just need to sum them over m times. Then you can get the following results. Okay, so now you can change this probability to an upper bound, and then to this equation here, and then you can see that there is a factor of m coming out when you try to evaluate the final hypothesis. Well, so what? Well, if you look at this equation, you say that, look, here you only have a half inequality applied to one hypothesis, and here you have the half inequality just apply repeat m times, and then you have an m there. Okay, apparently this m is just a constant. It does not appear to be a big deal, because as n goes to infinity, then the influence of m should be very small. The bad news is that m can be actually very large. In fact, m can even be infinity. Now, when can this m be infinity? You can think about what is m. M is actually the number of hypotheses that you have in your hypothesis set H. And so the m is the number of hypotheses. Now, think about the linear regression case, or think about the linear classifier case. How many hypotheses would you have in the linear classifier case, where you have infinitely many classifiers? They're all straight lines, but you have infinitely many of these slopes and also offset. So in this case, m would become infinity. So in a linear regression model, m can be infinity. Actually, in many classifiers, you have infinitely many hypotheses to choose from. Now, this is extremely bad news, because if m is infinity, then even if your n is going to be big, that is still not able to overcompensate the factor of m when m is really infinity. And so if m is infinity, is really big, and then that means your right-hand side, that bound over here, that would become not very useful, because the right-hand side would just become infinity. Now the good news is that we have techniques to upper bound the m. So we will do this later, but for now, let's look at the interpretation first. What we want to do next is to try to understand the meaning of this equation and try to draw some insight about this equation, because this m, you can see that this m here is trying to capture the number of hypotheses inside your hypothesis set. And so you can think it as, if my hypothesis set is very big, or you have a really complicated model, then you can imagine that the number of hypotheses will grow, and so m will grow. So m is sort of capturing the notion of how complex your model is. And in this equation here, n is capturing the number of training samples that you have, and epsilon is capturing what is the accuracy that you want to achieve. So you can see that now there's a clear trade-off between m and n and also epsilon. We want to try to analyze the relationship between these three together.